Today we're going to talk about cable and antenna measurement basics. So for the agenda today, and we're going to call it segment 1, our topics are going to be solving the problem, cable and antenna key measurements, RF basics for antenna system troubleshooting, key features of a cable and antenna analyzer, importance of regular calibration, why and how we do it. And then for next week, I'll give you a little teaser. It's going to be all about DTF, or distance default measurements. We'll talk about the setup for distance default, what you need to know to make a distance default measurement, how to interpret a sweep once you've taken it. And then I'll throw in a few tips and a few best practices. Continuing on, we'll talk about some things that are changing. Over the last 20 plus years, the use of radio frequency energy as a communication medium has exploded. Digitally encoded signals, Wi-Fi, digital FM radio, GPS, 3, 4, and 5G equipment is causing the radio spectrum to become congested. Frequency reuse in the broadcast, television, and radio bands has opened up more possibilities. Unlicensed products, from toys to home networking systems, has exploded. And all of these systems have put more pressure on the RF technician to be able to spot potential interference problems, maintain systems that operate to expected standards, avoid causing interference to other services. And radio frequency systems employ feed lines that are often not easily accessible. Some consist of hundreds of feet of coaxial feed lines clamped to a tower, held together with adapters and connectors attached to the antenna hundreds of feet in the air. Add in abnormalities such as bullet holes, animal remains, ice and snow, and incorrect installation. How do we fix this? By using a cable and antenna analyzer to perform key measurements. The key measurements that we'll discuss today are measure match, and this is a measurement to determine if there is a problem with your system. System impedance versus frequency is plotted on the display. You get your results back in VSWR or return loss. We have distance default, or DTF. This pinpoints the location of the problem. Distance versus frequency is plotted on the display. And you also get your results in VSWR or return loss. And finally, we have cable loss. And this is to determine how much power is being lost within the line or in individual components. The measurement may be called insertion loss, cable loss, or attenuation, and this is a manufacturer's specification. The benefits of line and antenna sweeping are test. It tests the overall integrity of an antenna system installation. And we can verify that antenna system components meet manufacturer's design specification and verify that antenna system meets the design engineer's design specifications. Pinpoint the location of antenna system problems prior to usage. And then finally, we confirm the system integration and antenna performance. You may ask yourself, why do I need a cable and antenna analyzer? Well, we use it for system commissioning. Antenna system commissioning is a process whereby faults and potential faults are eliminated before they compromise the system, prior to the system being put into use. It is structured and methodical, but also thorough, with the goal of having 100% system uptime for effective communications. We use it to troubleshoot existing antenna systems. When there is a problem, you can quickly read the system and determine where the problem is. And finally, we use it for preventive maintenance. Perform sweeps. Compare the sweeps saved during commissioning to see where changes may have occurred and fix potential problems before they take the system down completely. All components in a feedline system, including the antenna, must be matched in their characteristic impedance. Can anybody tell me what is the characteristic impedance we are interested in? We all want to make sure that all our components are matched to 50 ohms. Impedance matching, measure match, or simply match, it all refers to the same measurement. It's how well each of the components within a system are matched to the rest of the components. This is also measured in VSWR or return loss. I will talk a little bit about coaxial cable impedance. Feed lines are designed for a specific impedance, and as we learned from the previous slide, the impedance we're interested in is 50 ohms. Impedance is defined as the total passive opposition to the signal. It is a function of the diameters of the center conductor to the outer conductor and the dielectric constant of the insulating material between them. Changes in any of these dimensions will change the impedance of the feed line. Understanding what causes impedance changes is halfway to solving feed system problems. One of the fundamental laws of physics states, when load resistance or impedance is equal to the source's internal resistance or impedance, that maximum power will be developed in the load. What that says, in other words, is when everything in your system is matched, when you key up your radio, all the power will get out to the antenna. And I mentioned coaxial cable impedance is a complex function of the ratio of the diameters of the conductors. If the diameter ratio changes, the impedance of the cable will change and the power transfer changes also. These change from things such as a dent, a kink, deformation, too sharp of a bend radius, etc. If the transmission line and the load impedances are not the same, meaning they are mismatched, power is reflected from the load in the form of a wave traveling back to the source. Waves moving in the other direction towards the load, they interact, resulting in a series of standing waves along the length of the transmission line. A short or open will cause 100% of the power to be reflected. And we measure this in VSWR or return loss in dB. So here we have an example of our transmission line, and we have keyed up our radio and we have our forward power traveling down the line. And it hits some sort of a mismatch. It could be a dent, too sharp of a bend radius, or anything. And when it hits that mismatch, we get a little better reflected power. And you can think of a garden hose that has no obstructions and the water flowing flawlessly, no reflections. But what happens when the hose is kinked or the transmission line is shorted? We have a restriction of flow and all our power doesn't get out. VSWR versus return loss. What is it? What does it mean? I'll show you a little chart here. A perfect VSWR would be 1.0 to 1. That's a perfect match. A perfect return loss value is negative infinity. Both of these values mean that 100% of the power is delivered to our antenna. It's not possible because every component will have a certain amount of loss. If we have a VSWR of 1.43 to 1, that coincides with a negative 15 dB return loss. This also means that very little reflected power is present. 96.8% of the power is delivered to the antenna, and only a little more than 3% of the power gets reflected back. And that's not too bad. If we have a VSWR of 1.5 to 1, negative 13.98 dB return loss, or round it to negative 14 dB, that also means very little reflected power. 96% of the power gets delivered to the antenna, only 4% gets reflected back. And most antennas will be spec'd either between a certain frequency band at either 1.5 to 1 VSWR or negative 14 dB return loss. Those are the common goals, is to have everything be at that value. Now, if our VSWR or VSWR rises a little bit, we're up at 2.0 to 1. Notice our return loss drops to negative 9.54. That means about 89% of the power is delivered to the antenna, and we have about 11% reflected back. We're starting to run into a little problem area. It's not real severe, but you can see that it's going to start giving us issues. And if you rise up to 10.0 to 1 VSWR or negative 1.74 dB on the return loss scale, this is a very poor match. Only 33% of the power gets delivered to the antenna, and the rest is being reflected back. Think about it. If you have a 10,000 kilowatt, a 10 kilowatt transmitter, and only 33% of the power is delivered to the antenna, that means only about 6,700 watts is getting reflected back to your transmitter, and you're going to have some issues. So this is what it looks like, or a relationship between VSWR versus return loss. What are some of the things that cause an impedance mismatch? Well, there's a lot of things. You can have bad or loose connectors, water in the feed line, poorly or improperly installed ground kits, wind damage, corrosion, poor center pin contact, dents in the feed line, gouges, and my all-time favorite, bullet holes in the feed line. And for those of you that do have a cable and antenna analyzer, such as an SK4500 or SK6000, and if you have it in front of you, maybe you want to turn it on and possibly follow along. So I'll discuss some of the key features of the analyzers. They'll all do a measure match, give you a frequency response, and what this does, it'll result in a highly reliable assessment of the health of critical components in your system. It'll do a cable loss measurement, which measures the insertion loss of the cable system over a given frequency range. And then it will also do fault location or distance to fault mode, which indicates VSWR or return loss levels at each point along the cable and antenna system length. Some of the applications that this product gets used for are cellular networks, PCS, paging, tactical military, microwave, public safety, network coverage, and then there are several other applications it gets used for. So utilizing our SiteHawk analyzer, we can show you key functionality. Up here in the top left, this is where we would select the mode of operation by tapping right there where it's got the big red oval. And the different mode selections will drop down. The first one at the top of the list is SWR or VSWR. This gives you, this is a measure match sweep, and you'll get a frequency response in VSWR. The next one down would be return loss. This also is a measure match sweep, and you will get your frequency response in return loss. The next selection down is cable loss. This is a one-way measurement showing the loss of power from the beginning of the cable to the end, and you get your results back in return loss. We drop down one more, DTF_SWR. It's a distance to fault measurement. It'll pinpoint exactly where the fault lies, and you get your results back in VSWR. And finally, the last one, DTF-RL. It's distance to fault measurement. Again, pinpoints exactly where the fault lies, and you get your results back in return loss. Here I show an antenna sweep in return loss. The antenna bandwidth can be defined as its usable frequency range. It is equal to the difference between the upper and lower usable frequency. The frequency limits are determined by the antenna's VSWR or return loss. So a couple things to pick out. I turn my limit line on and I set it to neg 14 dB. And a lot of times I'm asked, why did you select negative 14? Well, the specification on this particular antenna is that it's actually, I believe, 796 up to 906 megahertz specification at negative 14 dB. So I turn my limit line on, and everything below that limit line in the yellow portion of the trace is passing. Anything above that's in the white trace would fail. I throw on a couple of markers that will help me determine where my low end frequency is and my high end frequency is of this band. And then my resonant band is right in the middle of these two markers. And if you look up towards the left portion of the screen, you see the yellow rectangle number 1, and right next to it, it says 781.0770 megahertz. It's at about negative 13.7 dB. And then marker 2 right below it is at 918.2113 megahertz and also at minus 13 dB. So my markers are just a little bit outside the neg 14 band, but I can say that this antenna is good from 781 to 918. Hey, if you don't like the return loss look, you can easily flip it over to SWR. And if you examine closely, we have our limit line set at 1.5. It automatically, when I switched modes from return loss to SWR, it automatically recalculated the value of my limit line from negative 14 dB return loss to 1.5 VSWR. My markers move down, and if you look, well, and the resonant band is in between. And take a look at the marker values up at the top left. Marker 1 is still 781.0770, which did not change from my return loss sweep. The only thing that changed is the SWR value was recalculated from the value it was, and I think it was like 13.23 to 1.56, and marker 2 is at 918.2113 megahertz at a value of 1.55 VSWR. So that's how you can easily switch. Just change the mode, nothing else changes. And this is what an antenna sweep can look like. A cable loss measurement would be the coax cables, connectors, and other devices. They all have loss. The loss is due to skin effect, radiation, leakage, conductor resistance, and dielectric losses. Cable loss is specified by the manufacturer, usually at 1 or 2 particular frequencies. So what you'd want to do for a particular cable, you would check the manufacturer specifications for their details. Distance to fault is a measurement of how far from the test point a fault occurs. The distance from the test point to a problem in the system. DTF includes all system components and displays the match characteristics of all the components on the screen of the analyzer in either VSWR or return loss units. DTF can check components individually or as an entire system. Thereby, when you check components individually before you haul, if you're going to replace an antenna at the top of a tower, you can actually sweep an antenna down on the ground to make sure that it passes before you go through all the trouble of dragging it up a tower, connecting it up, and then find out it's a bad antenna. In distance to fault, instead of hand over hand checking of the feed line up a tower, this device will give a distance to the problem. The field technician might still have to climb the tower, but he or she will have a much smaller area to check to find the fault. So when you're going to prepare for antenna sweeping, what do we need to do? we need to enter the frequency range of the antenna. You know, set the range a little bit wider than the specified range. Very important to go ahead and calibrate your analyzer. And then attach your antenna. What does the sweep show? The frequency response of the antenna. I mentioned calibration. Accurate measurements can only be taken with the analyzer if the calibration is accurate. Calibration tells the unit where to begin the measurement. So you can calibrate here at the test port, and this is where your measurement begins. Use the calibration combo, and when you do this, it defines where the SiteHawk ends and the attached system begins. And I have a little tip for you to use a test cable in your measurements. Instead of calibrating right here at the test port, adding a test cable will allow you to extend the test port to reach those hard to get places, kind of like scrubbing your back in a shower without a brush. So you add a 1.5 meter RF test cable. And also I want to mention that adding a test cable or changes in the length of the test cable will affect readings taken if you're in a distance default mode. But now what you want to do is calibrate at the end of the cable. And when you do that, you calibrate here, and this is where the test port is now and 0.0 on your measurement. And the test system, or the system you're going to test, will start right there. It's important to remember that changes in the frequency range entered will impact the cal, turning off the COR on indication. So prior to performing a measure match, cable loss, or distance default sweep, it's very important to calibrate the unit using a precision cal combo. The cal combo is a precision piece of equipment and must be handled with care. If it is dropped, the connectors could be deformed, not connectable to the analyzer, and if the internal resistor is broken, it will make the device unusable. So to recap, we discussed cable and antenna basics, some key measurements, some key measurement examples, and the importance of calibration.